Okay, partitions are like two halves, for example, of one single message log. And well, in case if there's only one consumer, Kafka cluster will send messages from all partitions to this consumer. So this is called balancing. So Kafka cluster will resolve it by itself. And the consumer is not even aware that there are many partitions. It doesn't have to be aware of it. It just connects a topic, which is divided into multiple pieces. And it can read from the topic, and Kafka cluster will manage sending from different machines to a single consumer, and it will look like just a stream of messages read from a single topic. But let's say another consumer joins the cluster. It is, for example, another instance of the first consumer. Okay, so now we have two consumers or two instances of the same consumer. And we can see that there is a special identifier called group identifier for each consumer. And in this case, both consumers are labeled group 1. This means that they are belonging to the same group. These consumers are basically two instances of the same thing. So if another consumer from the same group joins the cluster will balance and reassign partitions. This means that now one consumer will read from one partition and the other one will read from the second partition. So now we have two instances to the same consumer, and the data is read in parallel. So parallel processing is what Kafka is often used for, because there are often a lot of partitions in Kafka topics, like hundreds of or thousands of partitions. Okay. A part of automatic balancing, we can also do manual assignments. So if we want to say that consumer 1 should read from partition 1 and 2, and consumer 2 should read from partition 3, then we can manually assign, like hard code this assignment if we want it. So one of the most important advantages of Kafka is decoupling producers from consumers. Okay? Decoupling means that producers and consumers are independent on each other. So producers don't know about how many consumers there are. Consumers don't know about how many producers there are. They don't care. There is this persistent log between them, and that's what they care about. It's especially important if you use microservices and Kafka as your main middleware between these microservices. Because services should be able to come and go without disrupting the system, without knowing about the other services, the particular instances of other services. And a lot of projects go for microservice architecture, and Kafka is the default choice for the infrastructure between microservices. So as Jonas Bonner said, the most important stuff about microservices happens in between. Okay. Okay. The last important feature of Kafka is the way the consumers acknowledge reads. So we saw a consumer reading messages, but at some point the consumer has to acknowledge. It has to go back to the queue and say, I processed messages. So when you are consuming messages, you have to call commit. It's a special function on the consumer. And calling commit marks the offset where you finished the processing. In case of Kafka, the offset is the number, which means the place where we are going to start reading from next. So let's say that now our consumer goes down. This means that we have to, for example, spin a new node. So the fresh consumer will have the same group ID, group 1. And before the node went down, the last committed offset for partition 1 was offset 2. So the number where we should start reading from now is 3. And this is the place where our consumer will continue reading from, because it committed before it went down. It will carry on. Okay, so now that we have recapped the most important features of Apache Kafka, let's quickly go through Akka Streams. So this talk assumes at least basic knowledge on Akka Streams, but we will go through the simplest definitions. So Akka Stream is basically a DSL for describing data transformation pipelines and a whole machine materializer for running these pipelines. It uses actor model underneath, and it implements the reactive streams specification. This specification is a high-level specs for describing stream processing. It has been implemented in various languages. It defines a way and constraints how reactive streams should behave, and Akka Streams is one of possible implementations, the referential implementation, I guess. It focuses particularly on backpressure and asynchronous processing. This is very important in Akka Streams. And what is often underrated is its test kit. It comes with a powerful test kit. So testing asynchronous and parallel code is difficult. Okay? The test kit allows specifying test streams, test assertions in a simple way. The tests are short and simple, and test kit is really powerful. So it is a big advantage of Akka Streams. And it's also extensible, which means that it has ability to add custom stages, like connectors to different kind of technologies, which Akka Streams is, Reactive Kafka is an example of. So here's an example of processing pipeline, a stream. Typically, in Akka Streams, we have different kinds of stages in this stream. So the input stage is called source. The output stage is the sync, where our data leaves the stream after processing, and all the stages in between may be called flows. Flow is a special kind of stage which has an input and an output. And I'd like to mention also the Alpaca initiative. So Akka team announced around a half year ago, I guess, an initiative to gather as much connectors as possible. This means that it's some kind of a call to create more connector libraries, different kind of technologies. So the whole Alpaca initiative becomes like Apache Camel for reactive applications. So currently there are HTTP, streaming TCP, streaming file IO, S3, JMS, Cassandra, you name it, connectors, allowing connecting Akka Streams to selected infrastructure, and Reactive Kafka is one of them. Okay, let's say that this is your processing pipeline. So in many cases, you may want to ingest messages for processing, then Kafka will be your source. And underneath, it will use Kafka consumer from the plain Kafka API. And this source needs to be backpressure aware. This means that this source will emit messages only when the rest of the stream can process these messages. And you may as well need to send your processing results to Kafka. And in such case, you are going to need a sink. And underneath the sink, there will be a producer, which will save messages to Kafka and which will generate backpressure. This means that producer will send messages to Kafka, get acknowledgements that the messages are processed, that the messages are persisted in Kafka, and this will drive the main backpressure in this stream. And finally, there are many cases where Kafka needs to be a flow. You may need to put messages in Kafka and then carry on with further processing after the write is confirmed. So similarly to sync, such flow should do backpressure on writes. And these three stages are the main parts of the API provided by Reactive Kafka library. So I'm saying Reactive Kafka all the time, but the new official name is Akka Stream Kafka. It started as Reactive Kafka at SoftwareMill, and then the first users came, the library started to grow, And a great new developer joined the project, Alexei Romanchuk. And he has rebuilt the library. He has built the new API that you can see now. And then Akka team has joined, Patrick Norwell, Andrei Varga, and others. And since then, the library is rock solid and maintained by Akka. And, well, it still grows under the Akka ecosystem. OK, let's finally see some code. So you need, let's create the simplest stream possible. Let's say we want to read messages from Kafka into an Akka stream without committing for now. So this kind of source is called a plain source. Okay, so this highlighted yellow line is practically the most important part. It creates a new source subscribing to a particular topic, and the rest are just the next stages of processing. For example, some map async. The upper part is the boring part where you have to initialize consumer settings to connect to Kafka, which is not really very interesting, but it has to be there. Okay? So let's say you want to implement a similar thing using the plain API, just the Java Kafka API. So if you wanted to build this with the plain Java API, it would be, I'd say, less reactive. The main part here is the poll call. Okay, so consumer object from the Kafka API has a poll function, which is blocking, brutally blocking and waiting for a timeout to pass. In this case, it's 100 milliseconds. And after the timeout passes and there are no messages, we can repeat it. So basically, using Kafka directly requires from us to write a loop. So this is a simple imperative loop, processing messages read from Kafka. And let's say we want to add asynchronous processing to this, proper error handling, and some back pressure. Of course, there is back pressure here because blocking is back pressure. But if you would like to use some more sophisticated ways of back pressure, then I think that this whole thing would start to grow into something that would be basically reinventing Akka Streams. I cannot imagine any other way. So let's see what's happening underneath. From your perspective, it's just a source. Here on the left, there's a source stage of the stream, which gets a demand from downstream and sends messages. And there is a boundary in an isolated dispatcher. There is an Akka actor which does the blocking, dirty Kafka calls with the direct API. It sends messages to itself. This scheduled poll thing, it's like a self-calling in an asynchronous way to call the poll underneath. But you don't have to think of any of it. Okay? From your perspective, it's a source which is back pressure aware. And we have some statistics. This is plain consumer performance measured in two ways. The first one is just the plain consumer implemented with a loop that we saw as a first example. The second one is Akka plain consumer. And this number, 1,367,000, is messages per second. These are very small messages, but we can see that Akka plain consumer is pretty much the same, has pretty much the same performance in this case. Okay, but we mentioned committing, right? Usually, if we read messages from Kafka, we want to acknowledge back after processing. So we can then be sure that if the consumer comes back, or if a new consumer joins from the same group, it will read from where the last ended. So how do we do committing? So our source stage emits messages one by one. At least that's how it looks like in the API of Akka Streams. If you want to commit this, then this source will emit messages of special kind called Committable Messages. And each of this message has a commit function. So you can commit on a single message, and this will underneath send a message to this consumer actor, which does all the synchronization and calls to the Kafka API to manage commits. Because in Kafka API, commits have to be synchronized with poll calls, which is difficult to manage with a plain API. In this case, you don't have to worry about it. You have your messages, and you call commit on a message, which we will see in an example. So this time we create consumer.committable source. It's a different kind of source. This source produces committable messages, as I mentioned. And the first map async call will be some kind of processing. In this case, DB update may mean like updating database records with some data from the messages. And the second map async is the next stage of processing, is calling message.committable_offset.commit ScalaDSL. This means that we call commit on a message, and this goes all the way back to the consumer underneath. If we wanted to implement this with the Java example, we can do something like that. So there's our loop that we saw before, and we can add a commit sync call just after the processing, which is quite ugly because it's synchronous blocking. And if you wanted to use asynchronous committing here, we would have to deal with callbacks. So it quickly would start to grow and grow. But usually, we don't want to commit every single message. If we process a lot of messages, then it's OK to commit, for example, if we buffer some kind of batch of messages. Okay, so let's say I want to commit every message that passes the number 100. Okay, so 100, 200, and so on. So let's say we can create a buffer here. And if the buffer size exceeds the maximum batch size, then we call commit. Still, this is synchronous call, which we don't want to do. With Akka Streams, there's actually no need to add anything to our API. By our, I mean the API of the Reactive Kafka library. We can leverage different kinds of stages available in Akka Streams themselves. So Akka Streams has a stage called grouped within, which means collect messages until you collect 100 of them, or 5 seconds pass, whichever comes first. It's a very useful stage, which will just gather objects, and after the collecting is complete, it will send them as a whole list to the next stage. And in this case, the next stage is a fold left. Okay, so the group within stage creates a list, and the next stage folds this list to a single object, which is a committable offset batch. So this batch represents metadata, represents information on the 100 messages gathered in the previous stage. And then we can call commit ScalaDSL just once on this single batch. And this is the typical approach. Such approach allows us to have a delivery semantics of at least once delivery. This means that it is possible that the server goes down before we commit, and when the server comes up, we will reread messages and reprocess them. But it is guaranteed that the messages will be delivered at least once. There may be duplications which we have to deal with in a different way, but at least once delivery is often enough. If you need stronger delivery guarantees, there are ways to do this with our library too. And if we implement this with the plain Java API, so we would have results like on the left, like 1,600,000 messages per second. And the Akka batched consumer in the last version is pretty close to the plain version. It was much slower, but it started to be faster with a few great optimizations and with the new Kafka version underneath, apparently. So in this case, we think after the processing, we transform the messages to make them producer-compatible messages. We put them into the producer, which blocks, or I should say back pressures, because it's asynchronous. It back pressures on the writing to Kafka, and then the next stage would do commit, also asynchronously. This producer settings.parallelism parameter here in map async allows us to have multiple commits in parallel if we really need to fine-tune the performance. And finally, my favorite example is streaming streams. This would mean that we have a stream, and each element of this stream is a stream of a type that you can see below. So the type is source of tuples, and in each tuple there is some topic and partition metadata and a source. So it's stream emitting streams. In case there is a rebalancing in Kafka, so for example a new consumer joins, then this master source will emit new source underneath in form of notification that something changed in partition assignment. So each element of the upper source, or the parent source, I should say, is a pair of information about topic and partition. So we know for which topic and which partition, or a set of topics and partitions, is the inner source assigned and the source itself. So we can do processing for each source independently and have back pressure per partition or per set of partitions. Okay, the next thing I'd like to discuss is error handling. So there is some code underneath that would retry connecting to Kafka if there are problems, and you don't have to deal with it initially, but there are some retries, and after we exhaust all the retries, eventually this stream will fail, and we have to deal with it somehow. So the most common way is to materialize the stream. So if you call run on the stream, it will be materialized. It will produce a value, and this value would be a pair of two objects. One of these objects is called control, at least type of this object is control, and the other one would be a standard Scala future. So what we can do with the future is we can observe it, we can put a callback on it, and say future on failure, and then we can handle any kind of failure. Typically, if we catch an exception here, this means that the stream failed, and we basically don't. Akka Stream Kafka comes with Java API. So if you need to work on a Java project, and if you would like to use the library, there's no problem. The Java API is also very well designed, and there is an example here showing how we can do a committable source, committing messages in batches using the Java API. And this is Java, and it can still fit on one slide, which I think is a good sign. One more thing I'd like to mention is Kafka Streams. Who of you knows what is Kafka Streams? Okay. So Kafka Streams is another library. And this is a library for streaming processing built by the authors of Kafka. And often you may wonder if I should use Akka Streams library or if I should use this other one. So this library, I see that my time is up, so let's just quickly recap. The Kafka Streams library is in Java, not Scala. It's meant for stateful processing, windowing, joining, aggregation. So this is kind of different kind of stream processing. While Akka Stream Kafka is written in Scala, it focuses on back pressure, which is not well done really in the Kafka Streams library. It focuses on async processing, and the main thing in interoperability with Akka Streams. So if you use Akka Streams already, connecting to Kafka would be much simpler with Akka Streams Kafka. Okay, I think that's all I have prepared for you today. You can join the project. You can join our Gitter channel to ask questions. And if you have any questions for me, you can catch me later. Thank you very much. Enjoy the conference.
Thank you for the presentation. Sorry, we don't have the time, so if anyone has questions, please ask him later. じゃあどうも、プレゼンテーションありがとうございました。